For a hobbyist or someone wanting to build a machine to get it working and wanting it to work a bit better than just simply turning around, to be looking at is the relationship between the magnetic field and the pole face. So to get a piece of paper, we've got our permanent magnet, or what could well be a permanent magnet. And I'll draw it as a permanent magnet. Here. So we are going to have lines of flux that are flying like this through here, and then on the back of this around. That's not really particularly relevant for this particular case. And we are going to place a coil of wire inside here, and let's just say we make it a very small coil. Like this. And we pass a current through there. Current is going to travel like that. And as I've said before, with our current, we get a magnetic field. To make the machine work as best as it could, we want a very good match between the surface area here of this and the amount of coil that's within the magnetic field. If we've got an excessively large coil inside there, maybe something like that, and that's going to be trying to rotate in there, apart from the fact I've drawn it oversized and it would hit. You're finding out you've got a lot of mass here which is not inside and being affected by this magnetic field that's being created in our permanent magnet field. So it's effectively a waste. Okay? You want to consider optimizing, getting the relationship between the coil size and this to be close together. And in your coil, if you're having your coil to be wrapped around some form of laminated steel or some form of core, so again we can redraw this. Like that. If we're going to have a core, something that's going to be rotating in this field, we would ideally like the size of this to be roughly equal to the size of this. And I've got some machines that have been built, some first iterations of machines that students have built before they were aware of this, and then they've gone off and rebuilt them. And the first one is this one over here. And we can see in this machine here, we've got our permanent magnets and our very, very large coils that have been put in here, which is like this. So we pass a current in through our commutator through here. We set up our magnetic field here, but much of this magnetic field is not interacting with our permanent magnet. So it's a waste. I would argue the students in this case would be better to either increase the size of the magnet here to get closer to this relationship, or to reduce the size of the field to get closer to this sort of relationship. Whereas this one here is far too large. Again, if we look at a commercial machine, we can see that. Again, this is an induction machine, not a permanent magnet DC, but we see the same thing. We can see that the size of the length of the pole face in this particular machine is in the order of, if we use the laminations here, you can see that it's in the order of 2.5 centimetres, an inch, and similarly here, 2.5 centimetres to an inch. And this machine here, the lines of the lines of flux are being concentrated over a very short distance to the pole face or to the rotor. Again, if this is an induction machine, let's just pretend it's a permanent magnet DC machine like all the other ones we've been talking about. But we've got a very close relationship in the size here. So, in another machine that students have built, we can see that this relationship here is much closer. The size of this bolt face is very similar to the size of these magnets. This machine worked very well. It was quite efficient. Okay, we've got something similar to this. And again, similarly with this brushless DC motor, we can see in here that this bolt head that I've used to create the pole face here is very similar in size to the permanent magnet on the rotor.